Hi, welcome to an audio test session with APX. These videos provide worthwhile information for APX users and demonstrations on a range of audio measurement applications. In this session, Mike will discuss and demonstrate loudspeaker test methodologies.
Greetings folks, Mike Martin here with Audio Precision. Welcome to this edition of Audio Test Sessions with APX. In this session, we will be discussing typical loudspeaker test methodology, typical equipment configurations, and the software solutions that Audio Precision has produced to address this testing need. But before we jump into the details, let's take a quick look at the system in action. Here we will run the loudspeaker production test measurement set. Within 7 seconds of starting the test, you have a complete set of the most important measurement results for evaluating a speaker, including frequency response, THD, rub and buzz, impulse response, impedance, and teal small values, all without moving a single cable. This plot shows the measured frequency response for a very good speaker. Achieving this level of result is not just dependent on the DUT. It takes attention to detail to get the optimum results for a given environment. Next, we'll do a quick review of some of the methods used to perform electroacoustic test. Acoustic reflections are the nemesis of acoustic measurements. Perfectly anechoic measurements are not possible, but there are techniques that can dramatically improve your results, even in difficult conditions. The next 6 slides briefly cover each of the options shown here to help mitigate the reflections. Acoustic testing outdoors, technically called free field testing, can be done with excellent results. A wide open field, well away from reflecting surfaces, is ideal. The downside is that weather may limit when you can do your testing, and uncontrollable external noise sources such as wind, sirens, or jet planes may force retests. This photo shows 2 techniques being used simultaneously. Free field testing has been combined with the ground plane technique that we'll discuss shortly. Anechoic chambers provide very low reflection environments, but building a chamber is very expensive, and lower frequency coverage requires a very large chamber. The typical setup has a speaker and measurement mic mounted on tripods with a distance of 1 or 2 meters between them. This is the conventional elevated far field measurement. Ground plane measurements are interesting, as intentional reflections are produced, but these reflections are constructive and result in a 6 dB increase in sound pressure level at the mic for a given test distance compared to a standard elevated far field measurement. The measurement mic is placed flat on the surface at a distance that is at least 3 times or more the longest dimension of the DUT. This technique is a practical way to achieve good test results in a lab or office environment. Windowing uses DSP capability built into the test system to digitally shorten the measured time response to cut out some reflections. Shown in the upper left is an example of typical floor bounce. The timing of this bounce is very deterministic and, using the formula shown, can be calculated quite accurately. However, this technique is a bit problematic if the reflection time is short. Shortening the measurement window directly reduces the resolution on lower frequency response. In this case, you might be forced to make near-field measurements to acquire an accurate low-frequency response, and then merge the data sets together to produce a more accurate overall response plot. Audio Precision APX measurement software includes windowing, and one of the nice features is that you can move the window on the impulse response plot or the energy time curve and watch how this change affects the frequency response plot. You can easily see how big of an impact the windowing changes make on the measurement. For near-field testing, the microphone is placed as close to the center of the diaphragm as possible, while allowing clearance for the full movement of the diaphragm during the test. At low frequencies, the driver acts as a rigid piston. In this configuration, the reflections and noise are eliminated from the measurement, producing an accurate representation of the low-frequency response. However, this technique is only valid up to a few hundred hertz. So, to get a full picture of the speaker's frequency response, it is necessary to splice the near-field response with the upper portion of a far-field response. It is not unusual to combine some of these techniques to get the best results possible for a given situation. Here we see the basic functional blocks of the loudspeaker test system. Ideally, the flatness of the frequency response and the distortion of these items is significantly better than the device under test, so that the variations seen in the data are due primarily to the DUT. This is typically true of instrumentation-grade equipment. The sense resistor shown on the return leg of the amplifier is used to determine impedance of the loudspeaker. This is usually a very small precision resistance, typically in the hundreds of milliohm range. And of course, adding a computer allows for automation, as long as the instrumentation supports it. For the purposes of this video, I am using what might be considered an R&D setup, with an APX 525 audio analyzer and an APX 1701 transducer interface as shown here. The equipment provides all of the functions needed to perform loudspeaker testing. The APX 1701 is a two-channel device providing support for use of two measurement microphones and dual amplifiers, allowing for either single speaker or dual speaker measurements. This can be handy for production tests, where it's often desirable to be setting up the next device while the current device is being tested. As previously discussed, a near-field measurement can produce very good low-frequency results. The system shown here is configured to make both a near-field and a far-field measurement as parts of a single sequence. Note that I have shown an APX 526 analyzer here, which has 4 inputs, providing coverage for the 2 mic inputs and the sense resistor input. Shown here is an alternative solution called APX 500 Flex, which is targeted at providing low-cost test solutions for production tests through the use of third-party ASIO audio interfaces and other accessory items, rather than the traditional APX 5XX series hardware analyzers. This platform uses the exact same APX 500 measurement software that is used with the AP hardware analyzers and will produce results quite similar to those shown in the following measurements. One comment here: we know the frequency response of the measurement mic, which is stated by the manufacturer and/or contained in the TEDS data, but we don't know the flatness of the third-party power amp. It is therefore necessary to characterize the frequency response of the amp and create an equalization curve that calibrates out the amplitude variations based on frequency. Next, we will do a quick overview of the APX 500 measurement software user interface, then move on to perform setup and running of an acoustic response test of a driver, a loudspeaker production test of a driver, and as a bonus, a setup and test of a Bluetooth speaker.
Thank you for joining us for this audio test session with APX.